In this video, an artificial agent learns to control a lunar lander, adjusting its engine thrust through trial and error to achieve a safe landing. But what makes this video unique is that you don't just see the landings. You also see inside the agent's mind. Through animations, you can follow both the lander's behavior and how the agent's internal memory evolves over time, showing how it learns which actions lead to a successful landing. In the lunar lander problem, the rocket engine controls the thrust force acting on the spacecraft. This force affects its velocity. If the velocity becomes too high, the lander may exceed the maximum altitude. If it becomes too negative, the lander approaches the surface too quickly. Excessive speed at landing results in a crash. The goal is to land safely as fast as possible. Crashing gives a negative reward, while a safe landing gives a positive reward.
For the lunar problem, we use the Advantage Actor-Critic method. Compared to pure policy gradients, this makes learning more stable and efficient. The critic evaluates the action and tells the actor how good it was using an advantage value. The critic is associated with a set of parameters called W. The actor then selects a continuous action, and each experience updates both the actor and the critic. The actor is coupled to a set of parameters called C. So over time, we learn together, the actor improves its decisions, and the critic improves its feedback. So together, we form a perfect team.
The frame on the left represents the environment. It shows how the agent controls the spacecraft. It also displays information such as force, speed, and position. The frame on the right shows the agent's memory. Lighter colors indicate higher values. The lower plot shows the policy, force as a function of speed and position. The training now begins. The size of the fire beneath the craft is in proportion to the force. The animation is now paused to reflect. In these first episodes, the policy was random. Consequently, every episode ended in a crash. Now, we speed up the animation to fast forward the learning process. As you can see, the agent's memory is continuously updated. It becomes clear that the policy is changing. Let us test the agent after 3,000 episodes of training. It is still crashing, but there has been improvement. The crash is less severe. We can see in the policy plot that the agent increases force when the spacecraft approaches the surface with negative speed. Again, let us fast forward the learning process.
This is not only fascinating, it is beautiful. We can see that the agent's memory converges to an optimal policy in a way that almost seems supernatural.
A trained agent is now in place. The value function shows that approaching the surface too quickly causes a crash, regardless of the applied force. The function also shows that high positive speed combined with a large position will cause the agent to move outside the game area. The policy is in line with intuition. Apply high force when approaching the surface with high speed. Success. Now we can observe the desired behavior. The lunar lander touches down safely. The problem presented here is one of many example problems described in the book Reinforcement Learning Explained. This was only a brief description. Many more details are presented in the book. Please visit the book's homepage for more information.